Welcome to Empowered Learning. This video will be about using derivatives to be able to find out information about a function, which includes the shape of the graph of that function. So putting it another way, we are going to use derivatives to do curve sketching. Now, if you're watching this video, you should be familiar with doing some type of curve sketching, or as I say, knowing the graphs of basic functions for at least a good bit of the basic functions that you cover in a basic college algebra or pre-calc course. Those basic functions should include your function x squared, x cubed, cubed root, square root, 1 over x, 1 over x squared, your greatest integer function, as well as all of your basic sine, trig functions like sine, cosine, tangent, cosecant, secant, cotangent, and it'll be great if you know the graphs of their inverses as well. Okay, so all those functions, you should know what those basic functions look like. You should also be able to do transformations on those functions. Now, when we get into trying to figure out things like what I'm going to write here, so let's say we have some function y is equal to x squared plus natural log of x divided by square root of x plus 3. When we have functions that are like that, we're not really expected to be able to just look at that and say, boom, I know what that looks like. Okay. However, what we could do is we could study the first and second derivatives of this particular function and the information that the first and second derivatives give, along with basic information like what's the domain of the function, does it have any vertical asymptotes, horizontal asymptotes, holes in the graph, so on and so forth, along with those normal things about the original function that we can easily figure out. We could use all that information, compile it together so that we can come up with a sketch of what the graph of that function would look like. Now, thankfully, we have graphing calculators and online graphers that could actually do a lot of this for us. But it's important for us to be able to have this skill because we may be in situations where we need to kind of know some property of a function like this, and we're not going to have some kind of technology tool available to us, or which is probably the thing that you'll probably run into more, you may have some technology tool that will graph this for you, but because of the limitations of the technology that you're dealing with, it may not show you everything that you need to actually see. And so if you're trying to figure out, let's say, hey, is this point actually on the graph of this function? Your grapher may actually show you, it may appear that it is, but you may actually have a hole there. Or it may look like your function is actually, it actually has like a smooth dip or a smooth peak at a particular location. But when you zoom into it, you'll actually figure out that it's either a corner or a cusp. Okay. And so you won't necessarily know that unless you know something intimate about the properties of these functions. Okay, and we could find out information like that, even though it's a little tedious to do. We can find out the information of that these graphers don't really show us by doing the methods that we're going to talk about in this video. Okay, now to put this into perspective so that you'll know what it is that you should be able to do right now at a minimum versus what we're going to try to do. We're going to go back to a standard pre-calculus algebra or college algebra type problem and kind of show you, hey, if we had a polynomial that was factored out, we should be able to sketch a graph of it. And I'm going to show you that after we do that, how that differs to what it is that we're actually trying to do now. All right, so before I move forward here, if you are already familiar with how to look at polynomials in factor form like this and sketch the graph of it, then by all means, I would say go ahead and skip this portion of the video and go back to where we actually started to talk about some of the properties of first and second derivatives that we need to know. Okay, so if you're not familiar with this process, hopefully this will kind of bring back some memories, or jog something in your brain to where you'll remember how to do this. If we want to sketch a graph of this particular polynomial function here, where it's already factored out, one of the things that we need to know is where its x-intercepts or its zeros are, okay? The other thing that we need to know is that for each corresponding zero, we need to know this concept of multiplicity. How many times does a particular factor repeat in this function? Afterwards, we need to know essentially whether our function is going to cross through the x-axis, that's what the t means, or will the function be tangent to, or sometimes we say just touch the x-axis at each of these x-intercepts. And so we're going to note by the multiplicity whether it's going to cross or touch, okay? After we do that, what we can do here from the multiplicity, if we add up all the multiplicities, adding up all the multiplicities will give us n. And what n is for our function is a degree. And that tells us the maximum number of zeros that particular function could have. In this case, it'll be the maximum number of x-intercepts, okay? And then the last things that we'll need to know is what is the leading term of the polynomial, as well as the degree. And we're going to put all that information together so that we can find out what is called the end behavior, okay? So we see from our polynomial being in factored form, we have zeros at x equals -2, and I'm starting from the lowest and going to the highest because this factor has a multiplicity of 3. We also have x equals 4, has a multiplicity of 2, and of course we know that because whatever exponent here is on the factor, and of course I don't have another x minus 4 over here or another x plus 2 over here anywhere, so I know that for x minus 4 and x plus 2 respectively, that's it, okay? And then I have x equals 6, and that multiplicity, since I don't see anything here, is an understood 1, okay? And so I'm going to go ahead and bring this up here. So this will be in here. So this is in here, and of course it's going to equal the degree. So I'll just write it like that. All right, so we see here that the multiplicity is how many times our factor repeats, and we can see based upon the exponent of each factor what that is. And if we add this up, we'll get 6. So the degree of our polynomial is 6. So we'll put that here. If you remember, if our multiplicity is odd, and I'm going to start here with this 1. If the multiplicity is odd and it's 1, then it's going to cross through your x-axis here like a line, okay? The main thing is that it's just going to cross through. If it's odd and it's a number bigger than 1, like 3 here, it will cross through. And so I meant to just put, try to simulate what this actually is. So this is at x equals 6, so this is what it would look like there. Or it may look like this. At this one at x equals -2, it will cross through like x cubed because, of course, multiplicity 3, it'll look like this. So either cross through like this or cross through down there like that, okay? And if your multiplicity is even, then it's going to bounce off of or be tangent to the x-axis, kind of like how x squared is. We look at the graph of x squared. The graph of x squared looks like this. We see how it bounces off of the x-axis then. And so in knowing that, we now have a good idea of what this graph is going to act like as we draw it, just by knowing the multiplicities and the degree. The last thing that we need to know is what is the leading coefficient. And we see here we have a -3. So what this tells us here is if we were to multiply out this particular function, it would look like some rendition of -3 raised to the 6 plus, and then we'll just have a bunch of other stuff, okay? And as x gets to positive and or negative infinity, our function is going to act a lot like 3x raised to the 6. Now, -3x raised to the 6 is going to act a lot like -3x squared. And we know -3x squared would be opening downward here, okay? So x raised to the 6 would just do it like this, but faster. So what that tells us is that our end behavior here for values of x, positive or negative infinity, is going to have this end behavior like this, basically going to face down. So now that we know all that, we could use this information and actually draw our graph here, okay? All right, so here's our Cartesian plane. We're going to do x-intercept at -2, at 4, and at 6. I'll make sure I got right values, okay? And I also know here that I'm going to have end behavior that looks like this and like that, okay? All right, so now that we have that, we know that since our function here is a polynomial and it's going to be continuous for all real numbers, I know here that this graph's just going to be nice and connected all the way through, okay? And it's going to be nice and smooth as well. If we look at x equals -2, we see it has a multiplicity of 3, which means it's going to cross through the x-axis at x equals -2. So my graph is going to have to come from down here, up here, and cross through. So it's going to look something like that when it crosses through, okay? If I go back and look at x equals 4, the multiplicity is even, hence it's going to bounce off of the x-axis or be tangent to it, okay? So here at this point, my graph is here, and I got to come from up here back down and essentially bounce off of the x-axis here. So I know whatever goes on here, I don't know, but I know that it's got to go up, then come down, and then eventually bounce off the x-axis here at x equals 4, okay? And then lastly here at x equals 6, I know that my multiplicity is 1, so it's going to have to cross through, but cross through like a line, okay? And so here, if I cross through, I got to come up here, get back down, cross through like a line, and get back down here. So it's essentially going to look like this, okay? Now, when I connect everything together, my graph in general is going to look something like this, okay? And so that gives me a rough sketch of what this particular function looks like. Now, the reason I'm bringing this up here is because for situations like a polynomial that's in factored form, or let's say even a rational function, or maybe even a function that looks like this, let's say like a -2x minus 3 cubed plus 4, all of these basic type functions, we should be able to sketch a graph of them with relative ease, okay? Now, if we go back to what we were looking at earlier here, which we were talking about this particular function, notice that that's not going to be as easy to do as it was for this example that we just got through looking at here, okay? And hence, this is why we look to derivatives to help us to be able to figure out how a function that's like this, what its graph is actually going to look like, and to know intimately some of the properties along with it, okay? Now, what are some of the questions that looking at derivatives, and particularly first and second derivatives, can answer for us, okay? Well, the first thing they could answer is, when is our function increasing? When is it decreasing? When is it constant, okay? And of course, we can figure out this information by knowing what is going to be the slope of the tangent line at various x values, okay? If the slope of the tangent line is positive for certain x values, then for a function, then it's going to be positive. If the slope of the tangent line for certain x values for a function is negative, it's going to be decreasing, okay? And I said slope of tangent line here is positive. For our function is going to be increasing there. Slope of tangent line is negative, is going to be decreasing there. And when the slope of the tangent line is equal to 0 for certain x values in our function, then we know the function is going to be constant, which means it's basically going to look like a horizontal line, or it's going to have a smooth peak, smooth dip like that, okay? So that is to say, what x values does our function have the potential of having a local max or min, okay? So if you remember in earlier videos when we talked about local extrema, remember that the whole concept of a critical value, a critical number, let us know those locations. And remember how we actually said that the derivative of a function would either have to exist, so we have to get some real number, or it would not exist here. And that would be situations where we either have a corner or we have a cusp, to where that would let us know, hey, we either have a local max or local min there, okay? How can we determine when a function has no local max or local min, okay? Well, we're going to see something indirectly called the first derivative test, and also the second derivative test, that will answer this particular question here, okay? And notice that the first derivative test and second derivative test both are looking for the same thing. They're just doing it in a different way, okay? What they're looking for is essentially locations where we have a local max or local min, also known as a relative max or relative min value, okay? And then of course, there's this concept of this thing called concavity, and that's basically describing the shape of the graph. And so I'm going to get more into that later in the video. But by us knowing what the concavity of our function f will look like, that will allow us to be able to actually draw what the shape of that graph would look like for certain x values. And of course, the expectation here is that the concavity will change, for different intervals of x within the domain of our function here. And so we just need to figure out what those intervals are and when the concavity actually changes. Okay. And so these types of questions are really the heart of the concepts that we need to understand in order to be able to do what's called optimization problems. Okay, and that's basically word problems where we're either trying to minimize or maximize something. And if you need to be well versed on that, of course, you can watch my videos on optimization problems as well. We'll actually utilize this first and derivative test a lot in that video, more so than we will this one. Okay. So with that being said here, what we're going to do next is I'm going to try to compile all the concepts that we need to know of in block diagram form. I'm going to take a 30,000 foot view of it first, just to kind of give you some highlights on the concepts that we need to know to be able to, first of all, do the first derivative test and the second derivative test. And second of all, to be able to sketch the graph of some function, kind of like what we are considering here. Okay. Now we won't actually do this one because this one's a pain because I just made it up. But I'll give you some simpler examples so that you can kind of get a feel for what this is like. Okay. All right. So right now I'm going to show you this block diagram. And so what this block diagram is trying to do here is to show you how some of the concepts that we should have learned already and concepts that we are going to learn in this particular video all kind of converge upon this notion of doing the second derivative test. Okay. And so in short, what the second derivative test does, it uses a critical number or a critical value and second derivatives to be able to determine if an x value is going to be a location where you have a local min or local max. Okay. Your first derivative test will also tell us if a particular x value is a local min or local max, but it will do it by comparing when the function changes from increasing to decreasing or decreasing to increasing. Okay. So two different approaches to the same thing. Now for the first derivative test, the two main things that we need here are what we call a critical number or critical value, which we've already defined, and the increasing decreasing test. Okay. And essentially all the increasing decreasing test tells us is that if we are considering values of x for some function, if we take the derivative of it and we plug in, let's say, I'm just going to call it c here, certain values of x named c, and we end up with positive results, we know our function is increasing for these particular x values. As a matter of fact, I think I'll just stick to x there because that may make it a little bit more simple. So for the x values, for where I plug it into the derivative of the function and I get a positive result, I know my graph is increasing. If I do the same thing, but I get values for the derivative that are negative, then it's going to be decreasing. And of course, if I plug in values of x and it's going to be equal to 0, then it's going to be constant. But the increasing decreasing test doesn't deal with this situation, it only deals with this. Okay. Now, these two concepts here feed into what the first derivative test is defined to be. And again, we're basically just using a critical number to identify the potential places where we could have a local max or min. And we use this concept of plugging in x values around the critical value to see, does our function go from increasing to decreasing, from decreasing to increasing, or is it going to be increasing to increasing or decreasing to decreasing? And the only time that we're going to have a local max or local min is when we actually have a change from either increasing to decreasing or decreasing to increasing. Okay. Now for the second derivative test, part of the reason why I have this arrow here is because we're using this concept of the critical value, and that's flowing through to the second derivative test. So we are going to be able to, we're going to have to be able to find critical values to be able to employ the second derivative test properly. Okay. Now, on the other side here, we see that we have these definitions of concavity. And again, we are going to talk about what this actually means here on the next page here when I get to it. But this basically is just a shape of how your graph may look based upon the second derivative of your function. Okay. And I'm going to define concavity in a couple of different ways. When I go through those definitions, just know that whatever way resonates best with you, that's the one that you need to remember. Okay. You do not have to know all three ways. Whichever one works best for you, you're like, yep, I get that. That's the one you need to keep. The rest of them, throw away. Okay. All right. So the concavity test, after we know what this concept of concavity is, and I'll go ahead and tell you this part now. So whenever we have the second derivative of a function and we plug it in and it's going to be positive, we consider our graph to be concave up for those portion of x values for our original function. When our second derivative, we plug in an x value and it ends up being negative, we know that our original function was concave down, okay? And when we have second derivative of our function equaling 0, what we end up having is what we call an inflection point, okay? And so that's where this comes into play, okay? Now, what the concavity test does is essentially it does what we talked about here. I'm taking the second derivative and I need to know what values of x are going to produce concave up values, what values of x are going to produce concave down values, okay? And of course, with the concavity test, it really doesn't deal with this particular case, but we do need to know where concavity changes because that's important to us as well, okay? Especially whenever we're curve sketching. Now, of course, an inflection point is simply going to be defined as a place in our graph, or a point in our graph, rather, where we switch from either being concave down to concave up, or we go from concave up to being concave down. And again, I will show you pictures of what that looks like here in just a second. But knowing what concavity is, being able to employ the concavity test, knowing what an inflection point is, and also using the critical values from here all roll in to be able to do what we're going to consider to be the second derivative test. And again, this test is just having us use a critical value and information about our second derivative to be able to tell whether we have a relative maximum or a relative minimum at a particular x value, okay? All right, so next what we are going to do is I'm going to zoom in on this 30,000 foot view, and we're going to talk about the details of each of these blocks. And then after that, we'll do some examples and then some simple examples to try to warm us up, and then we'll get into the actual curve sketching part. All right, so this is what that block diagram would look like if I was to actually write in all the information that we need to know. And so I know it's small and I know that you probably can't read all of it, but I'm going to zoom in on each area so that we can read it, so that we can see what it says and sort of understand a little bit deeper what all of these concepts are that we are expected to know. All right, so I'm zoomed in, and the first block here is critical number. And again, a critical number is just a value, and we'll just call it an x value of a function f that's in the domain of this function, such that if we take the derivative of this particular function and plug in that value, c is either going to equal 0 or the derivative is not going to exist. And so to translate this another way, it's going to be a value of c in the domain of our function to where either if I plug in that value of c into the derivative is actually going to show either this way or this way that I have a horizontal tangent line, or it's going to show that the derivative does not exist. And so that could mean a lot of things in the case of the derivative does not exist. The cases that we hope that it comes out to be is we either have a cusp or we have a corner, but we could also see situations like we have a hole in our graph, we have a jump discontinuity, we also have, let's say if we have a vertical asymptote, it'll look something, not like that, but it'll look something like that. So, and of course, at this jump discontinuity, at this hole, or what we formerly call removable discontinuity, at this vertical asymptote, or even a vertical tangent line, here, at all these places, the derivative will not exist. Okay. So that is what a critical number is. Now, the increasing decreasing test, I'm going to zoom in just a little bit here. So the increasing decreasing test basically just tells us that if we find that the derivative of our function here is positive on some open interval I, and that's just of these x values that we plug into it. You give me x values, plug it in, the derivative is positive, then I know that my function is increasing on that interval. Similarly, if I plug in x values into my derivative and the x value and the corresponding derivative ends up being negative for all those values in this interval, then I know that my function is decreasing. Okay. And if we look at this graph here, we could kind of get an idea of why that is. So, of course, on the open interval from A to B and from C, try that again, from C to D here, we see that our graph is increasing. Okay. And if our graph is increasing, let's say if I took a point right here, we would see that the slope of the tangent line would be positive. And if I took a point right here, slope of the tangent line would be positive as well. For the interval from B to C, we see that, of course, slope of the tangent line would be negative there. And so from a computational standpoint, that is what we are trying to find out. All right, so now that we know what the increasing, decreasing test and what a critical number actually is, we can now use that information to find out what the first derivative test is. So using the concept of a critical number or a critical value and the increasing, decreasing test here, we can move on over and now talk about what the first derivative test actually says. And so I want to zoom out just a little bit here. So the first derivative test, and let me do this one more time here. Yeah, all right, I think that's a little better. So our first derivative test here basically says, using what we know about the critical value from here and the increasing, decreasing test there, if our function, if we take the derivative of our function and it changes from being positive to negative around some x value c, then we know that we end up having a local max at x equals c. Okay. So to demonstrate that, if this was the graph of my actual function f of x here, and notice that at this particular x value I would have a horizontal tangent line. Let's say at this point I know that the slope of my tangent line would be positive, and at this point the slope of my tangent line would be negative. So to put that another way here, we could just say that my function was increasing and now it started decreasing. Okay. Of course, here it would be 0. So if my function goes from increasing and then starts to decrease, I know that I have a local max at x equals c. Okay. Now, similarly, if my function looks like this, and of course I have a horizontal tangent line here, and if I pick a point here and a point here, I know that this particular point is going to have a tangent line that has a negative slope. This point is going to have a tangent line that has a slope. This point is going to have a tangent line whose slope is positive. So we go from negative to positive here. So my graph goes from decreasing to increasing. Okay. And so we know that at this particular point, which corresponds to a value x equals c, we know that it's going to have a local min because of that. Okay. Now we also see that in the case where our graph doesn't change as far as going from decreasing to increasing, or increasing to decreasing, we say that the first derivative test is inconclusive. And basically what that means is that we don't have a local max or local min there. And normally, not all the time, but normally what we end up having there is what's called an inflection point, and we're going to define what that is. An example of what this may look like for the case C situation is as follows. So let's say if we had a function that kind of looked like this, or let's say a function that looked like this, not necessarily this way. So basically what I'm trying to draw here are monotonic functions, where my function is either always increasing or always decreasing. So here, for this function, my derivative is always either going to be positive or 0. The only place where it may be 0 at is right here. And of course, before that, the slopes of the tangent line would be positive. Here, it would be 0. And then here, it would be positive again. Whereas here at this point, for this particular function, this one is pretty much always decreasing. If I had a point here, slope of the tangent line is negative. Had a point here, slope of the tangent line is negative. And here, slope of the tangent line is 0. Okay. So in the case of us having monotonic type of functions here, we know that, or let's say the portion of our function that we're looking at is monotonic. We know that in those situations, we're not going to have that switch from increasing to decreasing at a critical value. Okay. And remember, at all these points where we have the derivative equaling 0, that corresponds to an x value that is a critical value. Okay. And remember that we said that a critical value is a value of x that potentially has a local max or local min. And it's potential because of situations like this and this. Okay. Potential doesn't mean that we guarantee. Of course, in cases where we have the smooth peak or dip like this, or we have the corner or the cusp, yep, we know it's going to end up being one. But in these cases here, not so much. So what I'm showing here is basically if I had the graph of the derivative of the function. So this sort of curve that you're seeing here is actually the derivative of the function. If the derivative of the function lies above the x-axis, I know that my function is increasing. For this portion of the derivative of my function, since it lies below the x-axis, my original function is decreasing. Okay, so anytime the derivative of my graph lies above the x-axis, I know that the original function was increasing then. Anytime I know the derivative of my function lies below the x-axis, I know that my original function was decreasing then. Okay, and so we see the change here from increasing to decreasing. So this is how we know we have a local max. Whereas here, whenever we see our derivative being below the x-axis and then above, our original function was decreasing, then it was increasing. Now we see that let me erase that. So if we're going from increasing to decreasing, we have a local max. If we go from decreasing to increasing, then we have a local min. Okay, and that is what these two figures are trying to explain. Figure C here is trying to explain situations that could come up, one of which would be like these monotonic functions I was talking about here. This would actually be a situation like that, where the first derivative of our function always ends up just being negative here. It's either negative or 0. Okay, So that would go along with this particular situation here. Okay. All right. So now we understand essentially the first derivative test is just looking at a critical number. We want to see what is the behavior of the derivative before and after the critical number. Okay. All right, so the next thing that we need to do is talk about everything that we need to in order to understand the second derivative. So what we're going to do now is actually go down and talk about, and I'll go back here for a second. So we're going to talk about this whole concept of concavity first here, okay? And then we're going to work our way back up here to eventually talking about the second derivative test. All right, so for the concept of concave up and concave down, I have a picture of what that looks like here. But of course, I'm actually going to give you 3 different interpretations of it. So what this says here is concave up is going to be the graph of our function lies, the graph of the function lies above all of its tangent lines on some open interval I, okay? So as you can see here, here's your function, and all these tangent lines that I have here are all lying below the function. So when I can take a function and draw the tangent lines below the function, then I know it's concave up for that portion. So similarly, concave down, if I can draw all of the tangent lines above the function, kind of like what you see here, then the function is going to be considered to be concave down. Now, to make that a little bit more clear, I'm going to move to another page here so that I can draw that, and I'm going to give you the other interpretations as well. All right, so again, in this situation, if I have something that looks like this, this is considered concave up. If I have something that looks like that, that's considered concave down. I could also have something that looks like this, which is concave up. I could also have something that looks like this, which is concave down. And so here, just to kind of show you, if I draw these points here, 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 and here, and then you'll notice here, I will have to draw the tangent line below this curve here. I have to draw the tangent line below here as well. So that's why it's considered to be concave up. Actually, I'm drawing this the wrong way. Let me fix this. So what I meant to draw here was something that looks like this. Yeah. All right. And so in this instance for concave down, notice I have to draw the tangent line above the graph, and here again, tangent line above the graph. Okay. So that is one way that you can discern in between the graph, a portion of the graph of a function being concave up or concave down. Now, another way that we can do that kind of has sort of the opposite way of looking at it here. If I can draw a secant line through my function, like here and here, if I draw a secant line through my function, and notice that everywhere from this point to this point, if the graph lies below the secant line, then it's considered to be concave up. Again, from here to here, we see that the graph lies below the secant line. So the function lies below the secant line, so therefore it's concave up. course, it's just the opposite the other way. So if I draw the secant line here, if I have to draw the function, or the function lies above the secant line for this portion of the graph, then we know it's concave down. Same deal here. Draw the secant line here. Graph is above the secant line, so therefore it's concave down. Okay? So that is the second way that we can define concavity. So the last way I am going to define concavity, I'm going to try to use a little saying or analogy here. Okay? And so I'm going to do a concave up case and a concave down case to make my point. So this is actually probably the way that I prefer it, but if some of these other definitions work for you, that's great. So I imagine that if we take our function here, and let's say I had water and I wanted to pour water on my function. Okay, so let's say I took water and I poured it on my function. So here, when I pour it, if it's concave up, it settles in the cup. Okay, so concave up means water settles in the cup. Concave down means water rolls down. Okay, so we can see with concave up, if I was to pour water on this function here, it would settle in this cup that's being made. Whereas if I poured water on a concave down portion of the function, it would roll down the function for that piece. Okay. And so when we have situations like what I'm going to draw here, okay, where this portion is concave down, this portion is concave up, then you see how if I poured water on this function, for this portion, it's going to roll down. Concave down, water rolls down. But now that it switches to concave up, it settles in the cup. Okay? And so now you see what concave up looks like and concave down looks like, and you see how it switches for a function. And so I've drawn this here because I want you to realize that this particular point where the concavity switch actually happens, this is what we call the inflection point. Okay, it is the place where concavity switches. Or if we put it another way, it is the place where we know that our second derivative either switches from being positive to being negative. Okay, so it switches from being positive to negative, or vice versa. Switches from, and that's what this case is, switches from being negative to positive. Okay, so when second derivative actually switches, and on top of that, it switches at a place where we actually have a defined point on our graph, that is the definition of an inflection point. So my point, no pun intended there, is that the only place where we can have an inflection point is at an actual point on your function. So your function is going to have to be continuous, at a minimum, at least left-sided or right-sided continuous, for that to happen. Okay, we can't have a situation where we have a discontinuity at a place where we have an inflection point. Okay, now to make that clear, let's draw this particular function here. Okay, so this is rational function. Let's say this is at x equals 2. Okay. Now our function, we know for values that are less than 2, function is going to be concave down. For values of functions that are greater than 2, function is going to be concave up. We see that we have a vertical asymptote at x equals 2. We see that concavity switches, but I can't say I have an inflection point at x equals 2. I do not have an inflection point there. Concavity changes. It goes from second derivative being negative to second derivative being positive, but I do not have a defined point here. And since I don't have a defined point there, I can't call this place where I have a vertical asymptote an inflection point. All that I can say is that concavity changes there, okay? And that is the difference in between an inflection point versus just a location where concavity changes. All right, so now that we have a clear definition of what concave up and what concave down is, we're going to go ahead and move now and start to talk about this whole concept of a concavity test. Okay, and so I'll scroll down and let you see the rest of it later here. So the concavity test says, and I've mentioned this before, that if we take the second derivative of our function and we evaluate it for some interval of x values, for all those x values, if the second derivative is positive, we know that our graph is concave up. If we evaluate our second derivative for interval of x values and it's all negative for that, we know that our original function was concave down. Okay, so second derivative negative, concave down. Second derivative positive, concave up. And so here, if you look at this graph, you'll see that from the interval from A to B, this is going to be considered to be concave down, because remember, pour water on the function and it rolls down, concave down, water rolls down. And so you can see how that would be. And here we pour water on the function, concave up, water settles in the cup. From B to C, we know that our particular, and I don't know why that says this. Yeah, this is opposite of what it should be. So let me change this. Okay, so I went ahead and edited this. Yeah, so the second derivative should be negative from x equals a to x equals b, and it should be positive from x equals b to x equals c. So don't know why I flipped those values there, or those signs there, but that's what it is. So we have the concavity test here. Now, again, another thing I want to point out here is notice that at this particular point, point C, we notice that's where concavity changes. And if our original function actually has a defined point at x equals b, then we know that that will be the place where we have an inflection point. And that's actually what we're going to talk about next here. So I'm going to move on over. And again, we see that a point on the curve of f of x is called an inflection point if f is continuous at some point p. So this is our graph of our function f. We see that it's continuous at these points here. And f of x changes from being concave up to concave down, or vice versa. Okay. And so again, here we know that this portion of the graph is concave up. Here it changes, and then it's concave down. Here it changes, and now it's concave up again. Concave up again. And of course, P1 and P2 are going to be places where we have an inflection point. Okay. Now, just so that you know, whenever we talk about an inflection point, or another way of saying is where the second derivative is equal to 0, what we're actually saying here is that that's when the rate of change of the function actually stops changing. Okay. So here, if you notice that if I was to draw these points along this particular curve here, the slope of this line here, it starts off being really negative, then less negative, then less negative, then it ends up being 0. Okay. And of course, the slope of these tangent lines is the rate of change. And so as we can see, the rate of change, or the rate of the actual slopes changing, is getting closer and closer to 0 here. And of course, right at the inflection point, it is 0. Okay. And similar thing here. And that's just this particular case here. So the more common case that you'll see is a situation like what I'm drawing here, where let's say the slope of this tangent line is going to be a -2. Let's try to do that again. This is going to be a -2, where here is going to be a -4. And let's say here it is a -5. And let's say here at the inflection point, it is going to be a -7. Okay. Now, what we'll see here is that when it switches to be concave up, and I draw the tangent line, this may go back up now to be slope of tangent line is -6. And here, slope of this tangent line may be -3. So we see the most negative that our slope of the tangent lines get at point P2 would be 7. Whereas here, we see concavity switch, it actually went to 0. And so those are two different instances where you would actually see concavity switch. The main thing is that at the places of concavity, what you're going to see is that if your function is decreasing, then your function at the inflection point will be I guess either the most negative or the least negative, depending upon how it's acting. And of course, vice versa, whenever you're dealing with it being concave up. Okay. All right. So now that we know what an inflection point is, now we can actually talk about what the second derivative test says. Okay. So let me go back here just a second. So we've talked about this whole concept of concavity. We've talked about the concavity test. We've talked about inflection point. And we already know what a critical value is. And we see how that's filtered over from the first derivative test. So now all these concepts come and roll in to talk about what the second derivative test actually is. Okay. And so the second derivative test simply says this: if we have a solution to the first derivative of our function equaling 0, so remember this just means we have a horizontal tangent line, okay? So if we find that at x equals c, we have a horizontal tangent line, and it can either look like, this situation here or this situation here. And on top of that, we know that the second derivative of our function at this value c that made our derivative go to 0, aka at this critical value that made our made our first derivative go to 0. If we find that plugging in the critical value into the second derivative gives us a positive result, we know that we have a local min there. All right, and so if we look at this, this makes sense because we'll take this particular situation here. We know that this particular graph here, and we're saying that this is our function f. We know that it's concave up because pouring water on the function makes it settle in the cup. And notice here, since this is concave up, we have horizontal tangent line here at x equals c that meets this condition here. And concave up at a critical value means I should have a dip in the graph, aka local minimum. Okay. Similarly speaking, if f prime of c is equal to 0, meaning that I have a horizontal tangent line at x equals c here, okay, and on top of that, I know that my second derivative is negative. If I get that, then I know those two things tell me that the original function not only has the potential of having a local max and local min there, but it is going to be a local max because of the fact that the second derivative lets me know that my function here is concave down. So concave down with a point that has a critical value tells me that I'm going to have a local max there, okay? And so these are the things that we need to know to be able to not only sketch graphs of functions, but also be able to solve optimization problems, okay? All right, so now I'm going to go through a few warm-up examples just to kind of exercise all these concepts that we've learned. And then afterwards, I'm going to start a part 2 version of this video so that we can actually go through some of the curve sketching examples. Okay, so what we have here is this figure A, and this is a graph of some function from x equals 0 to x equals 8. Just for clarity here, let me try to draw this. I'm assuming here at 1, 2, 3, 4, 5, the x equals 5 here, this function lays flat before it goes back up. So it's kind of doing something like this. So at x equals 5 here, my graph's going to be flat like that, and then it's going to turn up and then turn down. It's kind of hard to draw it, but that's what's happening there, okay? All right, so what we want to know is for what values or for what open interval of x values is my function going to be increasing, okay? Now, notice here I'm looking at the original function, so we could just use what we know about functions increasing and decreasing to be able to do that. Not hard to do, okay? So here we know that starting off, since my function is going up like this, it's going to be increasing. It's going to increase starting at x equals 0, and it's going to stop at x equals 1. Now, remember from pre-cal or college algebra that anytime we say a function is either increasing, decreasing, or constant, we do it with an open interval of x values. That always is the case, and we do that because of the definition of increasing, decreasing, and constant. So we look here and we see from 1 to 2, our function's decreasing. From 2 to 3, our function's decreasing as well. But now we see starting at x equals 3, our function starts to increase again, okay? So I'm going to do union, and this function will increase again up until it gets to x equals 5 here, okay? Now, notice that at x equals 5, remember how I said this function flattens out, okay? So that means right at x equals 5, the slope of the tangent line going through that function right there is going to be 0, okay? And notice here at x equals 1, how right at x equals 1, we have a point that could have a horizontal tangent line as well. And notice that we did not include 1 in this interval of x values where it's increasing, okay? So because this flattens out, I can't include that either. So here I have to say from 3 to 5, but I also know from 5 onward it's going up again. So here what I'm just doing is taking out the number 5. Because exactly at x equals 5, my function is constant because it flattens out or it has a horizontal tangent line. And so the same thing happens at x equals 1, but in all these other places, from 0 to 1, from 3 to 5, and from 5 to 8, my function ends up increasing. Now, that being said, it'll be kind of easy to answer the next question. For what open interval of x values is f decreasing? Well, we only know it was one interval where it was decreasing, and that was from 1 to 3. Okay. Now, when is the graph of our original function, which is what we're looking at here, when is it concave up? Okay. So we know from 0 to 1, since we see it kind of has this concave down shape, that's not going to work for us. Okay. As a matter of fact, I'll go ahead and we'll answer both questions at the same time here. So we'll say x equals here, x equals here. So we know from 0 to 1, this is going to be concave down. Okay. if we keep on going, we say it's still concave down up until it gets to 2. So we actually need to change this and say that it's going to be concave down all the way from x equals 0 to x equals 2. Now at x equals 2, we see that the shape of the graph starts to switch. And now what it looks like it looks like it's going to be concave up now. And it's going to continue to be concave up until we get to x equals 4. So we say from 2 to 4. So from right here to right here, our function is going to be concave up. So we're saying concave down here, and from here to here is concave up. And then, of course, from x equals 4 to x equals 5, for that small little portion right here, from x equals 4 to x equals 5, we see that small little portion there ends up being concave down again. So this little small portion here is concave down. So we'll come back here from 4 to 5, concave down. And then, of course, from 5 onward, on up here, we'll see that our graph ends up being concave up again. So from this point to this point, of course, our graph's going to be concave up again. So we'll just say from 5 to 8, it'll be concave up. Okay. All right. So hopefully you understand how we picked out whether the graph was concave up or concave down, and how we express that in terms of open interval of x values there. All right. So let's look at our second. Oh, sorry. I need to do this one last question here. So what are the coordinates of the inflection points? Okay. So remember, inflection points are the places where our concavity changes. And so I'm just going to actually write those down here. I'm just going to call them IPs. So places where our concavity changed. Well, we see here, I'm going to put this in blue here. We see here, concavity changed. Here, concavity changed. Here, concavity changed. So that first point is going to be the point 2, 2. The second point here is going to be the point 4, 3. And the third point is going to be, looks like the point 5, 4. Okay. So we see those are the 3 places where we had inflection points. All right, so now let's look at the second example here. So note that for this problem, we are not looking at g of x, okay? We are not looking at g of x. What we are looking at is the second derivative of g of x, okay? And so if you remember, the second derivative of some function g of x that we don't actually know what it looks like, what we do know is when the function is going to be concave up and when it's going to be concave down, okay? So since this is the second derivative, we know that whenever the second derivative is positive, it's going to lie above the x-axis, okay? We also know that whenever the second derivative is positive, our graph of the original function is going to be concave up, okay? Whenever the second derivative of our function lies below the x-axis, that lets us know when the original function is going to be concave down. So when we see that, we know these intervals for which the graph of our original function will be concave up by finding the intervals of when the second derivative lie above the x-axis, okay? And we'll find whenever the graph of our original function g of x is concave down by figuring out when the graph of the second derivative is below the x-axis. And we will also find out the places where we have inflection points whenever we see that there is a change in concavity. Put another way, we will see that there is a change in the second derivative going from below the x-axis to above, or above the x-axis to below. And so our first question says, state the x-coordinates of the inflection points, okay? So in other words, state the x values where that happens. Well, we know that here, here, and here are the three potential places where we have inflection points, okay? The only two that actually satisfy our conditions here are this first one and this last one. This one in the middle doesn't work because if you remember here, we have to actually have a change in concavity, meaning we have to go from below the x-axis to above the x-axis, or above the x-axis to below, okay? Here we went from above, hit the x-axis, and went back. So there's something going on here, but it is not an inflection point, okay? So if we want to know the x-coordinates for the inflection points, it is going to be at x equals -2 and at x equals, let's see, that's 10, 9, 8, 7, 6, and at x equals 6, okay? Now, remember, we just know the x-coordinates, meaning the x value locations of where that is. We would have to know what g of x is so that we could plug in -2 and 6 into it to figure out what the actual point would be, where the actual inflection point would be at on the graph of g. But since we don't have that information, not much we can do, okay? Now, we also want to know where is our graph concave up and where is it concave down, okay? Concave up, we know anytime our second derivative is strictly above the x-axis here, okay? So let me erase this. Now notice that our graph is strictly above the x-axis for values of x that start at x equals -2. So it starts from here, keeps on going till it gets to x equals 2. So everywhere in between here. And then it starts again right after x equals 2 and keeps going on till we get to x equals 6. So here, if we want to write the answer to that question, it will be x will start at x equals -2, keep on going until it gets to 2. And then afterwards, we'll go from 2 on to 6, okay? Now, where is our original function g of x concave down? It's wherever the second derivative is below the x-axis, okay? And notice that here for all these values that are smaller than -2, graph is below the x-axis. For all these values that are greater than 6, graph is below the x-axis. So here we would have to say from -infinity to -2, and then union from 6 to infinity. That will be the case. That will be the x values for where our original function g of x, which again we don't know what that explicitly looks like, will be will be concave down. Same place where the second derivative lies below the x-axis. Okay, so this will conclude this part 1 video for studying the information that derivatives gives us to figure out the shape of a function as well as other properties of a function. The part 2 video that I'm going to do is going to go into the actual curve sketching. So I'm going to do 3 examples of curve sketching and then quickly run through some other examples that I've already worked out, and they're really just for show, but I just want to show you, how involved they could actually get. But the 3 examples that I'm going to work out with you, together, that should be enough to kind of give you an idea of how to approach this particular skill. All right, I'll see you in the next video.